Today, we're very pleased to feature Dan Wertheimer, who's the co-founder and chief scientist of the SETI at Home project and directs other UC Berkeley SETI searches at radio, infrared, and visible wavelengths, including the search for extraterrestrial radio emissions from nearby developed intelligent populations. I'm sure you'll hear more about that. He is also the principal investigator for the Worldwide Collaboration for Astronomy Signal Processing and Electronics Research. Please join me in welcoming Professor Wertheimer.
No, thanks. Thanks a lot. Thank you. So I wanted to talk to you about this question, is anybody out there? Are we alone? And you probably know that the field is called SETI. SETI is the search for extraterrestrial intelligence. And I thought I'd start by talking a little bit about early ideas for how we could communicate with ET. So the mathematician Carl Gauss, 200 years ago, suggested that we get in touch with ET by making large geometric structures. A big right triangle of pine trees, 3, 4, 5 miles on a side, a big square of dirt, wheat, water, and ET would look down with their high-resolution telescopes and see that we knew about the Pythagorean theorem, and then hopefully get in touch. And this was a clever idea, and unfortunately wasn't funded. Von Littron, also a couple hundred years ago, suggested that in order to get in touch with ET, we dig a large ditch 20 miles across and fill that circular ditch with kerosene and use this match, not to scale, to make a bright ring of fire, and ET would see this bright circle of light, and then they would get in touch with us, and it met with a similar fate. And then Charles Crow, 150 years ago, suggested that we get in touch with the Martians by using large mirrors to reflect the sunlight to the Martians, and actually several mirrors to outline the shape of the Big Dipper, Ursa Major, one where he lived in Paris. And I think you can guess what happened with that project. The first funded project was to send pornography into space. This was a plaque on the Pioneer 10 spacecraft, many of you remember. It was very controversial because these guys are naked. Originally, they were holding hands, but people were worried that they thought that we were one creature instead of two. So, these on the bottom of this plaque is the solar system with the sun and Mercury, Venus, and then Earth and the path of the spacecraft. And these are directions to pulsars, so they'll know where we live and they can come and eat us if they want to. Anyway, that was the first funded project. Then came the theoretical approach. It's called the Drake equation, and you can calculate the number of civilizations in our Milky Way galaxy, and all you have to do is multiply all these parameters together. The problem with the theoretical approach is we have no idea what any of these numbers are. I'll give you a hint how this equation works. It's kind of a whittling down process. You start with the number of stars in the galaxy, about 400 billion stars, and then you say, well, how many of those stars have planets? And then as you go along, the next factor is how many of those stars how many of those planets are good planets? So they have the right environment, they have the right temperature, liquid water, things that you need to make life. And then as you move further along the equation, once you have good planets, on what fraction of those good planets does life actually get started? So you have the right environment. We think life gets started pretty often because it happens pretty quickly. It happened pretty quickly here on Earth. And then once you get life started, how often this L is life, I is intelligence. What fraction of those planets where you get life started does intelligence evolve? That took a long time here on Earth, about 4 billion years. And the near last factor is C, the fraction where you get communication technology that develop lasers or radio or some way that we could communicate with them. And then the last factor is how long do they live, the longevity of the civilization. So our sun has been around about 5 billion years. Some stars are 10 billion years old. Our sun's going to be around another few billion years. So you can imagine very advanced civilizations, or they might blow themselves up quickly. As soon as they develop communication technology, they might also develop weapons technology. So we don't know how long civilizations are going to live. So we can't really do it the theoretical way, so you got to go out and look. One of the factors I mentioned in that equation was how many planets are there out there. And if you'd asked astronomers 20 years ago, are there planets going around other stars, they would have said, well, we really don't know. We think so, but we don't know. But that's all changed. As many of you know, now we know that most stars have planets going around. And then the first planets were found by this technique called the Doppler shift, where the planet, as it goes, the reason that it took so long to find planets going around other stars is they're little dinky things, right? Earth, 1 million Earths could fit inside the sun. So you can't really see the planets directly, but you can see them indirectly. As the planet goes around the star gets pulled on by the planet, the star wiggles a little bit. And so here's the planet going around, and the star wiggles. And you look for that wiggling motion. It doesn't wiggle by much. The sun kind of moves at walking speed because of Jupiter, the biggest planet in our solar system. So this motion, when the star goes away from us, it gets a little redder. When the star goes toward us, it gets a little bluer. And you can detect those subtle color shifts. But it's very subtle. But here's an example of this up and down motion. Actually, this is 2 planets. This star is moving up and down slowly. That's because of a distant planet, and it's moving up and down quickly because of a close-in planet. And so that's how the first planets were detected. And now, more recently, NASA sent up a mission to find planets a little differently by means of when the planet gets in front of the star. If you have good eyes, you see this little dot. If a planet gets in front of the star will dim a little bit, not by much. And so that's why you have to do this in space. But the starlight might dim by a part in 1,000 or something like that. And so what this thing does is it just basically a camera that just takes pictures of 100,000 stars every few minutes, and it looks to see if any of the stars are dimming down. And that would tell you if there's a planet. And now they found a few thousand of these planets. Here's a little diagram of the field that they're looking at, and the colors indicate the size of the planet. And they can even find now Earth-sized planets. They don't dim the star very much because the Earth-sized planets, the little rocky things, don't dim the star very much. But they're beginning to find these Earth-sized planets. And now it looks like there are more planets than there are stars. There's probably 1 trillion planets in our Milky Way galaxy. Here's another little picture of some of the Kepler planets that have been found with different kind of orbits and things. And you can see a lot of them are multiple planet systems, things with 3, 4, 5 planets going around their stars. Now we may even have life in our own solar system. And probably the most likely place for this, there are a lot of likely places, but the most likely place I think is probably this moon going around Jupiter called Europa. And the reason I and other people are excited about this is because this is a cutaway view, and there's ice on top of Europa, but underneath the ice is an ocean. And this, maybe there's something swimming around down there. This is liquid water, even though it's covered with frozen water. It's heated by these tidal forces. Now the problem is this ice on top is about 50 miles thick, and we're trying to figure out how to drill down or melt our way down or something to get in there and see if there's something swimming around. Now we don't know how life got started, but we think in something like this, the primordial soup. And people have done experiments where they kind of simulate the early conditions of Earth. And then what you do is you take a little flask and you put in some methane, ammonia, water, hydrogen, and you simulate lightning with some sparks. And you don't get gorillas crawling out of this thing, but you do get the basic building blocks of life, the amino acids and things that you and I are made of. So we're beginning to understand how life got started. And I mentioned it didn't take long for life to get started here on Earth. As soon as the Earth cooled down, some primitive, single-celled things popped up. So that's an indication that it might be a common process, the fact that it happened here quickly. So, if there is life out there, how are we going to get in touch? So one of the ideas is that Earthlings are sending off radio and television and radar signals out into space accidentally. The early television shows like I Love Lucy left the Earth 50, 60 years ago and have now gone past about 10,000 stars. And so this is a plot of television power leaving the Earth as a function, this is a log axis, as a function of time. And you can see we're getting brighter and brighter at television frequencies as we construct more television transmitters. And the Earth is brighter than the sun now at television frequencies. And so the nearby stars have seen The Simpsons, and so we're polluting space with our radio signals and our radar and navigational beacons and radio, FM radio goes right through the ionosphere. So what if we're doing that? Maybe, if we're lucky, ET is doing that as well, either sending us a message deliberately or maybe accidentally. So we're starting to look for these signals. This is a message that left the Earth intentionally that was transmitted in 1974, a sequence of zeros and ones, And if you turn those zeros and ones into black and white squares, if you're clever, you get this image with the telescope and the solar system with the sun and Mercury, Venus, Earth tipped toward this person, and a DNA molecule and some amino acids and binary numbers. Everybody see all that? So we're looking for these signals, either an artifact of their technology, something that accidentally leaves their civilization, or maybe, if we're very lucky, a deliberate signal, because they want to get in touch with us. And we think if they send us something deliberately, they'll make it easy for us to decode the message. That'll be anti-cryptographic. It'll contain pictures and language lessons and start off with some simple mathematics or something. Because there are a lot of old stars out there that are maybe 5 billion years ahead of us, it's likely that the first civilization we contact will be 1 billion or 2 billion years ahead of us. We cannot find them right now if they're primitive civilizations. If they're still trees or bacteria or even fish on their planet, we can't find them. We don't have the technology to do that. So it's much more likely we'll find one of these advanced civilizations first. So I'm not the first guy to think of this. There were the early radio pioneers, Tesla and Marconi, 100 years ago, both did experiments looking for signals from other civilizations. And actually, both of them found signals, and they got all excited, and they thought they were listening to signals from other civilizations. Actually, they didn't know it at the time, but they were listening to distant lightning bolts that bounce around in the ionosphere, and they eventually get to you get these whistler noises, and they heard these kind of whistling noises, and they thought that was a message from ET, but it was actually lightning. And now there are different groups, not just our group at Berkeley, although of course Berkeley is the best, but there are other groups doing this kind of work. There are our colleagues at the SETI Institute in Mountain View. There's a group in Australia, Argentina, Italy, and there's a few groups looking for laser signals at Harvard and Lick Observatory. Anyway, we use these big radio telescopes. The signals are likely to be weak, so we use these big antennas. This one is 300 feet across. And while we're using this telescope, this is what happened. And you might ask, how did that happen? How did that telescope get demolished? And the answer is, according to the World Weekly News, the aliens did not want to be discovered, and they zapped the telescope. And this is a telescope we were using right at the time when it was zapped. And so this zap theory is kind of an interesting idea. This is another telescope that we were using up at Hat Creek Observatory in Northern California. It's a UC Berkeley observatory. And while we were using this telescope, the same thing happened. That's what happened to that telescope. So now we're using the world's biggest telescope, testing this zap theory. This is the Arecibo telescope in Puerto Rico. And this telescope is 1,000 feet across, the world's largest telescope. And if you ever get to Puerto Rico, I recommend you visit. It's really spectacular. The radio waves bounce off this mirror up to a cryogenic receiver up here at the focus. And you can move the telescope around. You can't move the primary reflector, but you can move the receivers around. You can cover about a third of the sky. This thing holds about 10 billion bowls of cornflakes, although we haven't actually done that experiment. You might have seen it in the movie GoldenEye, James Bond. And in GoldenEye, it's actually, they say it's in Cuba, and it comes up out of the water. It doesn't really do that. And it's not in Cuba. And you might have seen it in the movie Contact, which was originally a book written by Carl Sagan, and there's a movie with Jodie Foster. And Carl Sagan used to work in our group and knew a lot about SETI, and so that book is pretty accurate, except that Jodie Foster found ET and we haven't. So there's a small group here of people at Space Science Labs and some in the engineering and astronomy departments. And there are students from physics and astronomy and engineering working together to do these SETI experiments. We have sponsors, the National Science Foundation, NASA, and we have a lot of individuals who help us out with donations. And we have a lot of companies that help us out, typically with equipment that we need to do these kind of searches. And we're trying to do searches at different wavelengths. We have telescopes that work in the infrared and at visible wavelengths, and we use these different radio telescopes to cover as much of the electromagnetic spectrum as we can. It's hard to predict what frequency ET might use. We're just getting in the game. You can see we don't cover these things very well. the search is like looking for a needle in a haystack. There's so many places to look in the sky and so many frequencies to cover, and we don't know what kind of signal they might be sending, AM, FM, what kind of signal type it would be. And so we're just getting started, but I'm optimistic in the long run because it's kind of limited by technology and computing power, and of course that's growing with Moore's Law. So I think right now we'd be very lucky to find them, but we're learning how to do it, and the capabilities are growing quickly. So we have a bunch of different searches at Berkeley, and I think the one I'm going to tell you a little bit more about is the SETI at Home search, because it involves the public. A lot of you might have heard about it. We have radio searches. We have visible searches. We're starting to do infrared searches, looking for different kinds of signals, pulse signals, signals that are on continuously, and we use different telescopes. We were funded by NASA originally, and NASA requires that you use acronyms. So SERENDIP is the Search for Extraterrestrial Radio Emissions from Nearby Developed Intelligent Populations. So this is one of the telescopes we're using in West Virginia. It's the largest steerable telescope, the Green Bank telescope. It's 100 meters across. And we've been using this to look at some of these Kepler planets that have been found. And I mentioned the Arecibo telescope. The reason we use this telescope is because Arecibo can only look at about a third of the sky. In particular, it can't look at the Kepler planets. They're too far north. But this Green Bank telescope can look almost anywhere in the sky, although it can't reach the further south places. At Arecibo, the radiation comes off the primary mirror and bounces off a secondary, tertiary mirror, and then there's a beautiful receiver up at the focus. The problem in SETI is one of the problems is we don't know what frequency to look at. So we want to listen to as many channels as we can simultaneously. So these are different frequencies, and this is a strong signal at one of the frequencies. And that's the kind of thing we're interested in. Is there some strong signals, like just kind of tuning your radio dial across the spectrum, looking for the signal strength meter to peak up? Except we don't want to look at one channel at a time. We don't want to tune here and then look, and then tune there and then look. So we build these multi-channel spectrometers, basically doing Fourier transforms, FFTs, so we can look at many, many channels at once, like having a billion different radios, each one tuned to a different frequency. Oops, I'm sorry. I somehow hit the wrong button and went to the end of the talk. I hope you didn't see that. Where were we? So I think we're here. Then we wanted to look for signals that weren't constant in frequency but drifting signals. So this is an example. This is frequency and time, and these are, if you have good eyes, you can see these drifting signals that, and not saying at a constant frequency. And we think this might happen because if you have a transmitter on a planet and the planet's spinning around or going around its star, introduces these accelerations. So we're going to look for these signals. And you can see these things with your eye, but we have about 100 million of these things to look at every second. So it's a kind of a difficult computational problem. And then we also want to look for pulsing signals, a bip, 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 bip. And that's actually a little harder to see with your eye, so I've circled them here. This repeating pulse pattern at kind of an unknown pulse period, an unknown rate, drift rate, unknown slope. So we want to look for those things too. And we have about 100 million of these things to look at every second. So what we did is we recorded the data coming from the Arecibo telescope, the world's largest telescope. We have about a petabyte of data that we store at NERSC, the National Energy Supercomputing Center here in Oakland. And we just store the data, and then later we process it looking for these different kinds of signals. And the way we process it is we ask the public for help. The public downloads this SETI at Home screensaver, which is a little program you can install on any kind of computer, Linux, Mac, PC, whatever you got. Then what happens is once you install that program, the program will go out over the internet, connect to our server up the hill here, and you'll be assigned a little piece of data from the Arecibo telescope. And everybody gets a different part of the sky or different frequency band to work on. So you'll get one part of the sky, you'll get another part of the sky. And the screensaver wakes up when your computer's not busy and starts going through that data looking for an interesting signal. Here it's found a signal that rises and falls and matches the Gaussian pattern that we'd expect as the telescope moves across a star. You'd expect it to get stronger and weaker and trace out one of those Gaussians. Anyway, it looks for interesting signals. And then I think I have a little movie of what it looks like when it's running on your screen. Anyway, I recommend you download this and help us hunt for ET. And then when it's done finding the interesting signals in that little piece of work that you've been assigned the work unit, it'll upload the results, any strong signals that it found, to our server up the hill. And your name is attached to that data. So if you're the lucky one that finds that faint murmur from distant civilization, you get the Nobel Prize. But there's a catch. The catch is that the Nobel Prize is about $1.5 million. There are 8 million people that have downloaded the SETI at Home screensaver. So you have to share it with everybody, so you only get about 20 cents or something like that.
But the parking spot you get to keep?
Yeah. The parking spot. Yeah, so I think, as most of you know, if you get the Nobel Prize, you get the blue sticker that you hang in your car. That's what you really want. You don't want the $1.5 million. You want that parking permit. And that's kind of the main motivation why I do the SETI. So I don't know how we're going to take that parking permit. I think you get 2 if you get the Nobel Prize. I don't know how we're going to break that up into 8 million. So anyway, the participants so far contributed about 3 million years of computing time. It used to be the biggest supercomputer on the planet. And I think it's the biggest computation that's ever been done. 3 times 10 to the 23 operations so far. Right now it's actually a few teraflops. It's not 1,000 teraflops. People are continuing to sign up, and the computing power keeps increasing because people are constantly upgrading their computers every few years. People buy more powerful machines. It's like having 8 million system administrators out there. Now, if you participate in SETI at Home, you can participate as an individual, but you can also participate in a team. You can join one of the teams, or you can make your own Citrus team. There are primary school teams, secondary, junior colleges, university, small, medium, large-sized company teams, and the teams compete with each other in somewhat friendly ways. Here's IBM has donated 2,000 years of computing time so far. And this competition has led to some bizarre behavior. Like some of these guys, and they're all guys, by the way, there are no women, they build these computer clusters in their basements. And you can go to this website, setifarm.org, and you can see these people that have built these computer clusters to rack up the SETI at Home units so they get more credit than the average person, do more work units. And here's another guy who built a SETI cluster to do SETI at Home, and I don't know why he's got these bolt cutters. Here's more bizarre behavior. So this guy, he's got a big cluster, and he's done 7,000 SETI at Home work units, and he's going to auction off his work units and transfer the credit that he got over to your account if you win this auction. And then you'll look really good, a unique chance to join the elite top 0.18% of all SETI users. So you don't have to actually have a fast computer. You can just buy work units. This went for $275. The website's very popular, a couple million hits a day. The thing I'm proud about, we haven't found ET, but the thing I'm happy about is that it engages a lot of people, and especially kids. We developed a curriculum with the Lawrence Hall of Science, because this question, are we alone? The kids participate in SETI, and then there's this curriculum, and this question gets kids interested in science, and it touches on all kinds of different science topics like biology and evolution, chemistry, how life got started, and they can learn astronomy, and they can learn a little bit about computers and physics. So it's a good hook to get kids interested in science. So this SETI at Home project led to a more general purpose public participation supercomputing. We developed an open source platform where people could put in their own projects, not just participate in SETI at Home. We call it distributed computing or edge resource aggregation, taking advantage of all the computing power out on the edges of the internet. We also call it the democratization of supercomputing. We developed this infrastructure led by David Anderson in our group called BOINC, Berkeley Open Infrastructure for Network Computing. And you can plug your own project, and there's 100 different projects you can participate in, not just SETI at Home, but you can allocate how you want your computer to be used. There's some medical projects. You can look for cancer drugs, HIV drugs, malaria drugs. There's a bunch of physics projects doing gravity wave research. There's global warming research, climate prediction. And you can say you want 20% of your spare computing cycles for SETI and 30% for cancer research. You pick the ones you want and pick how much computing power you want to dedicate to those projects. This is SETI at Home screensaver. This is the climate prediction screensaver. This is the Gravity Wave project, Einstein at Home. This is a protein folding project called Rosetta. Anyway, I would encourage you, if you're interested, to loan your computer cycles out. And the idea is that there's already about 1 billion machines out on the internet, and most of them are privately owned. If you get 100 million people, you get 100 petaflops. And you also get a lot of storage, exabyte of storage, which is kind of a tricky thing. You don't have to pay for it. That kind of distributed computing led us to develop citizen science projects called Thinking at Home. We call it Thinking at Home. And our first project was called Stardust at Home. These are projects that computers are not particularly good at, but our brains and pattern recognition, our visual system is better at, and so we wanted people to get engaged in things that computers are not good at. And this Stardust at Home, our first project, here we go. So we launched a spacecraft. This was largely built up the hill at Space Science Labs. We launched a spacecraft out near Jupiter to collect particles of dust that were around when the solar system was forming. We wanted to find out what those particles of dust were made of so we could find out how the planets form. We also flew it through a comet so we could find out what was in the comet. And it collected these particles of dust, and then it came back to Earth, and it scooped up these particles in this aerogel, this very low-density foam. And these little microscopic particles are somewhere in here, but we thought we'd need like 1,000 students looking through a microscope for years to find all the little microscopic particles so we could analyze them. So instead what we did is we put the aerogel on a scanning microscope, an automatic, and we took millions and millions of pictures, and we sent them out to the volunteers and asked them to find the particles, and they found a bunch of these things. This project is called Stardust at Home, and they found things we never would have found, and we're starting to analyze the particles and learn how the solar system formed, how planets formed, and how what the comets are made of, thanks to the Stardust at Home volunteers. So this is using the way you work is you download this kind of virtual microscope, and you take a little training course. What do these things look like? What are the false alarms? And then you look in these images, and you can focus around and move around, and you can find these little particles of dust. And then you get your name on the paper if you find a particle. Now there's a lot of these citizen science projects. Some use our platform. A lot of them use different kinds of platform. And there's a new thing we're working on, just starting off, called Energy at Home, where we're trying to get kids to, this may be of interest to citrus people, we're trying to get kids to go and do an energy audit of their home. Use one of these power meters to go and measure everything that's plugged in their house and find out how much their TV takes, how much energy their TV takes when it's on, when it's off, their stereo, their refrigerator, anything that they can measure that plugs into their home, or maybe use a smart meter, and then do kind of an energy audit of their home and compare with other homes, and also upload information about all the appliances so you can find out which TVs are energy hogs and which TVs are energy efficient. So we're trying to get kids interested in energy and people interested in energy, and that's one of these citizen science projects. But we're just getting started on that. It's just kind of more of an idea right now. We're just thinking about it. We've got a little website. If you're interested, I'd like to talk to you. Let me get back to SETI for a little bit. We're doing these optical searches, looking for laser signals, and we're doing that at a nearby telescope in Orinda. We're also doing it at Lick Observatory, which is near San Jose. And we're also doing it at Keck Observatory, which is in Hawaii. And we're just starting off using a telescope near Los Angeles, looking for an infrared. It's actually 3 telescopes looking for infrared laser signals. Infrared is maybe a good way for interstellar communication because it goes right through the dust in the galaxy. The radio goes through the dust, but visible light gets absorbed in the dust. That's why you can't see the Milky Way. It looks kind of blackish out there. Anyway, this is kind of a summary of all of our searching so far. 30 trillion fruitless tries, but scientists keep searching for ET. Actually, now we're up to 10 of the 18 fruitless tries. If you count all the different channels we've looked and places we've looked and kind of things we've tried, and we haven't found anything. We haven't bagged any aliens. But I'm actually optimistic in the long run. The reason I'm optimistic is because I think we're just getting in the game. We're learning how to do this, and Moore's Law is going to allow us to do much more thorough searches. But this is a plot of all the searches that we've done and other groups that are doing SETI have done as a function of frequency and how much of the sky these searches have covered and how sensitive they are. And what I want you to notice on this plot is there's a lot of uncovered search space. So if ET is broadcasting out here at 10 gigahertz or 100 gigahertz, nobody's looking at those frequencies. We're just covering a small range of radio frequencies right now, maybe a couple other frequencies. very little searching, maybe a billionth of the search space has been covered so far. So there could be radio signals going right through this room right now coming from other civilizations, either deliberate or unintentional signals. We wouldn't know. We'd be pointing in the wrong direction, listening to the wrong frequency. So it's not, we cannot say anything about how much life is out there given the searching that we've done so far. The universe could be completely teeming with intelligent life, we wouldn't know. Or it might be completely devoid. So we don't really have a clue. But I'm optimistic in the long run. I'm optimistic because all the computing power keeps getting better and better, and the technology, we're building a big telescope. Well, I should say the Chinese are building a big telescope, even bigger than Arecibo. This thing is 500 meters across, called a FAST telescope. We've been working with Chinese, and they've sent us some students to work with us, and my students have gone there a few times to try to figure out how to build this telescope and do SETI experiments in the mountains in southern China. There are some new ideas for these very wideband receivers. This is developed at Berkeley by Jack Welch that can cover 1 to 15 gigahertz all at once. A beautiful receiver that covers a very wide band of frequencies simultaneously. There are these new ideas for radio telescopes where you can look at many, many places at once. This is called a phased array feed, and if you add up all these different antennas with different phases, you can point the telescope essentially simultaneously to different places in the sky. It takes a lot of computing power, though. And so we're trying to figure out how to do that. And one of the new ideas is instead of making these giant telescopes, try to make a big telescope out of lots of little telescopes. And it turns out that's actually cheaper. The cost of a telescope goes almost as the cube of the diameter because of all the structural support. It's really more of a cube, a box, to support that dish. And so if you can build a telescope out of lots of little tiny telescopes, you can make it much cheaper, except the computing costs go way up because now you've got hundreds or thousands of receivers, and you've got to connect bring all those signals together. So we're trying to figure out how to do all the digital signal processing. So I think the next generation of telescopes is going to be built out of thousands of small dishes. And this is a plan for a thing called the Square Kilometer Array, which is a big international project that will be made out of maybe 4,000 dishes. And our group is trying to figure out how to do the computing for all that and combine all the signals. And this is an early prototype in South Africa. You put these things far away from people. There's a big desert in South Africa because you don't want other radio signals. You don't want cell phones and things like that near them. So this is a plot of the cost of one of these big arrays, the Square Kilometer Array, as a function of dish diameter. You'd like to make it out of small dishes. The cost of the dishes, the blue thing, goes up as you go to bigger and bigger dishes. But the cost of the signal processing, the computing, goes way up as you go to smaller dishes because it goes as the square of the number of dishes. So we've got to figure out how to get this computing cost, this orange part, down so we can figure out how to build telescopes out of lots of Dickey telescopes. But we're going to need petaflops of computing to do that. So that's one of the things our research group is working on. And we're trying to do it with kind of FPGAs and GPUs and connect everything up, make it look like a Linux cluster, even though it's made out of specialized hardware with 10 and 40 gigabit Ethernet. This is one of the boards that we worked on with the Berkeley Wireless Research Center, part of the engineering department, with FPGAs on it and a bunch of Ethernet. This is another board that we designed with high-speed ADCs and FPGAs. And so we're trying to learn how to process these signals. And we started this collaboration for radio astronomy signal processing, and we've got a lot of partners all over the world who are working with us to try to figure out how to do this powerful kind of signal processing. So we haven't discovered anything with ET, but that work has led to, the people used our SETI instruments for a number of really cool things. We made the first image of a black hole at the center of the galaxy using instruments that we developed originally for SETI. Using instruments we developed for SETI, we found a diamond planet made out of solid diamond. We're not sure how to get to it. I don't know how you compute that. It's bigger than the Earth, so it's a lot of carats. And a lot of women are asking me about this. So I mentioned I'm optimistic in the long run. This is a plot of the number of channels in the spectrometer as a function of time. We used to listen to 100 channels at once, and now we're listening to billions of channels at once. So it's growing. Capabilities are doubling every year. I don't know if that trend is going to continue. This is a plot of computing power as a function of time. And right now, computers are about as smart as a guppy or a lizard, maybe. And if that trend keeps going, we'll get to the singularity in 2030 or 2040, and then we can do some serious computing and do some serious SETI and do a much more thorough search. So don't hold your breath, but might happen in our lifetimes. Now, what if ET is not sending radio signals? We don't know how to do this now, but the Europeans and the U.S. are working on some kind of mission in space where you combine light from different telescopes, and you can take the spectrum of the atmosphere of an extrasolar planet and find out what's in the atmosphere. And if you, this might be 20 years away or something, but if you found oxygen in the atmosphere, that would tell you there's photosynthesis going on. So that would be a way we could discover primitive life. Right now we have to insist on technology. They have to have radio or lasers or something that we could see, but they have to be pretty high tech. But this might be a way to discover primitive life if we can detect oxygen or other signs of primitive life in the atmosphere of a distant planet. This is even further away that if you want to build a really big telescope, the sun focuses light or radio signals. You know, the light, Einstein figured out the light bends around things, and the sun is a big thing, and it bends around. And so you can use the sun as a lens called a gravitational lens. And the problem is that would be a huge telescope. That would be a telescope the size of the sun. The problem is that it focuses way out there beyond Pluto. An AU is the distance between the Earth and the sun. So this is 1,000 AU. So you got to get your camera or your receiver way out there. We don't know quite how to do that. But if you could do that, you could read license plates on an extrasolar planet. So this, I don't know if this will happen in your lifetime, but it's kind of an exciting prospect. So if you've been asleep the whole time, this is the only slide you have to pay attention to. The summary is that we haven't found ET, no ET so far, and we're still working on it. If you're interested further, there's this fun little thing you can watch on our website called The Great Debate. And Jeff Marcy and I had this debate about are we alone, and we talked about what the pros and cons are, and we went back and forth, and it's a lot of fun to watch, and you can vote on who you think won after you watch the video, and I hope you vote for me. And finally, I wanted to end with some poetry, some haiku. So the people that participate in SETI at Home, they've helped us enormously in many different ways. It's a big open source code. The programmers help us write the code and optimize the code and port it to a lot of platforms, get the bugs out of the code. It's largely written by volunteers. There are people that send in money. There are people that donate equipment that keeps the students going. There are people that have composed music, write literature, and then there are people that send in haikus. And there are thousands of these haikus that people have sent. I won't read you all of them. I'm just going to read you two of the haikus. Paula Cook at Duke University, searching for life, answers are revealed about ourselves. And last slide, Dan Seidner, 1 million Earthlings, bounded by optimism, leave their PCs on. So thank you very much.
Thank you for a great talk. Do we have any questions from the audience about how to join, what they can do?
Okay. Hi, Dan. When I was a kid, I had this book called The Quest for Extraterrestrial Intelligence, I think by Goldsmith or something. It's a kind of compendium of things. And I remember an article in there about specific places in the spectrum you might look based on arguments about life. So does it make sense to look everywhere, or are there places in the radio spectrum that make more sense?
Yeah, so there was in the early days of SETI, it was like impossible to look at all these different spectrum, and so we had to sort of guess what we call kind of a magic frequency band. And the idea was, as you know in your question, the idea was if ET's sending a deliberate signal, is there something that they would pick that we could also pick without talking to each other ahead of time? And we call it magic frequency. And one of the ideas was that hydrogen, the most abundant element, radiates at 21 centimeters, 1.4 gigahertz. And so maybe they would radiate at that frequency. So the early SETI searches said, okay, let's look around hydrogen. And then other people said, well, why would they send something at hydrogen? Because that's where all the astronomers are looking to map out the galaxy and all this stuff. Why would they pollute that one frequency that, in fact, on Earth, you're not allowed to transmit at that frequency. It's the one kind of protected place for astronomers. And so somebody said, well, how about hydroxyl OH? Because hydrogen, and then somebody said, well, what about 2 times hydrogen? What about pi times hydrogen? And then, so you can think of a zillion things, and how to outthink them is a complicated thing. So we think that the right strategy is probably a multiple strategy. You know, we don't really know what ET's doing, and if you look at our history of, you know, the early slides that I showed, the guys with the Pythagorean theorem, and those were good ideas at the time. Fire, and so maybe in a couple hundred years, people will just be laughing at what I'm showing, and it'll be one slide. And so I think the right strategy is to try to do a lot of different things and not just try to assume that we know what another civilization will do. So we kind of spread our activities out.
Dan, hi. Suppose you lived on one of the typical Kepler planets and you had Earth's technology. Could you see Earth?
So Earth sends off a lot of different things. It would be very hard to find television signals, because television signals, it's a megawatt, but it's transmitted omnidirectionally. So it leaves the Earth, but because it's transmitted omnidirectionally, we could only detect those on the very nearby stars with our, if we knew there was something there, we concentrated, looked for a long time, then we could dig it out maybe on a more distant star. But we don't do that. We kind of scan around. We only spend like 20 seconds at each place. But now Earth sends off much stronger things. The military has these things called BMEWS, Ballistic Missile Early Warning Radar Systems, looking for incoming missiles. The Russians have them and we have them, and they're sweeping across the sky. And it's much more beamed. And so you'd get, if they had something like that, you get this kind of pulse thing as it sweeps through you. And we could detect that out to maybe 100 light years away. And then the most powerful thing that is sent by the Earth is that Arecibo telescope. Is not just for receiving, but it also has a transmitter on it for radar to map Venus and Earth and map other planets and asteroids and things like that. And that's a megawatt transmitter, same as television, but it's beamed, right? So that's another factor of 10 to the 7th. And we could detect that transmitter on the other side of the galaxy, 100,000 light years away. So we could talk to, 100 billion stars, but they have to send us they have to beam in our direction. And it would take 100,000 years to get here and 100,000 years to get back. So it's not the kind of communication like, hi, how's your mom? It's more like, please send us your Library of Congress, all your music, poetry, literature, science, medicine,
Are you that well funded?
Yeah, that's a problem. This is kind of, there's not much money for SETI. I think there's only like 20 people on the planet that actually spend some fraction of their day doing SETI.
I'm interested in the relationship between SETI at Berkeley and the SETI Institute.
Yeah.
What their connection is genealogically, and also how their work today is related. So SETI is the name of a field like biology, and there are several people doing it. And the SETI Institute is a very good group of people in Mountain View. There's groups at Harvard, Italy, Argentina, and Berkeley has the largest group, and we have a lot of different kinds of searches. The SETI Institute has been very good at what we call targeted search. They've been concentrating at radio, at this hydrogen band that there was asked about earlier. And they do the advantage of doing these targeted searches, where you pick stars that you think might have life or planets that you think, is that you can spend a long time at each star. And so they've been doing a very good search on that. They're struggling for funds right now. It's a little more, their model is a little different from ours. We try to get NSF and NASA grants, and they're trying to get private money. And I think that's hard right now because of the economic downturn. But they've done really good work in the past, and we work closely with them. We have a lot of ideas and people going back and forth, and instrumentation ideas and stuff like that.
Do we have any other questions? Well, just want to thank you again for a great talk. Thank you.